Well, this should be a fun session because my name is Phil Cannon. I work for USDA Forest Service, State Project Forestry, and one of my jobs is to help administer the grants program we have for Southern Oakdale. And I made a rough guess, and between Susan and myself, Susan Frankel, who started this program back in about 2002, I think. We've had over 250 different grants. And there's been pretty stiff competition for grant funding. I'd like to acknowledge Bruce Molson for being very generous and helping rally the troops in Washington, D.C. to support this program. But there's been a lot of competition, so we can't do all of the projects that we get proposals for. And I'm very happy to report that one of the proposals that we could not support was anymore. We supported it for about 3 or 4 years, was the one that's going to be discussed next. So let's see, we're going to have Anna Conrad come up and talk about disease resistance and coast live oak. And while she's coming up, Anna, where are you?
Here.
Oh, good. Okay, so while she comes up, I'd just like to say that these guys found so much resistance in this coast live oak that we decided that it was probably okay to not worry about it anymore. And so as a result of their success, they didn't get funded. Kate, can you go up and get us oriented for this topic?
Thanks so much. Well, we'll say so much resistance is a relative term, and we'll agree to disagree on that fact. But so my name is Anna Conrad. I'm currently a postdoc at Ohio State University, working with Enrico Bonello there. So today I'll talk about some work that we've been doing over the last 9 years in another East Bay Regional Park called Briones Regional Park. And specifically, we've been examining the incidence and distribution of resistance in this coast live oak son of death pathosystem. This is actually what I'll be talking about today, is a smaller piece of a larger study that we initiated to examine pre-infection or constitutive levels of chemicals in coast live oak to identify these chemical biomarkers of resistance that we could then use to hopefully predict resistance in this susceptible species. So today I'll be talking about coast live oak resistance to Phytophthora. The work that we've done over the last 9 or so years, the phenotype for resistance in the species. Resistance, of course, is a relative term, and I'll be talking more about that. Next, I'll discuss some work that we did to actually examine the spatial distribution of resistant coast live oak over broader landscape scales within Briones Regional Park. And then I'll talk about incidence and natural infections. So, as I said, this study was initiated in 2010. At that time, in our study areas, there was, we consider these trees to be naive, or there was a relatively low disease pressure. So we're kind of right at the front of the disease spread. We chose that because we wanted to study the chemical composition of these trees before they were exposed to heavy doses of the pathogen. But it gave us a unique opportunity to examine resistance within this context. So past studies that have looked at resistance may have potentially underestimated the proportion of resistant trees if the most susceptible coast live oak had already died. In addition, it allowed us to look at the incidence of natural infections in these same sites in coast live oak to see how is it changing over time, and maybe make some conclusions as to some factors that could be influencing that incidence. So, as Phil mentioned, we found resistant trees, and not only in this study, but in past work in part done with Bryce and others. So it's not new that resistant coast live oak can be found in forests. And the proportion of these resistant coast live oaks can be relatively high. In some cases, about a quarter or a third of the coast live oak areas have been determined to be resistant. So, as I mentioned, we're interested in looking at resistance within live oak. So our objectives of our current study in Barones were to phenotype coast live oak for resistance via artificial inoculation with pathogen. Then we wanted to examine the spatial distribution of resistant trees. There's past studies to suggest that there was a genetic component to resistance, and so we're curious to see could we see resistant trees clustering together, or are they kind of randomly distributed across the landscape? And finally, we wanted to look at the incidence of natural disease development. So here's Barones Regional Park, which is here on a map of the Bay Area. I know it's kind of small, and we had actually 3 different sites within Barones, but I'm going to be focusing on work that we did in Seaborg site and Tabletop. So when I talk about phenotyping for resistance, what do I mean? So what we did over the course of 7 years, so in this case, trees were artificially inoculated with Phytophthora in 2010. Then starting in 2011, so approximately 1 year following inoculation, we started to visit each tree annually. And we did this actually up until last year, so 2018. But the results I'll be presenting today come from 2010 to 2017. So based on our annual monitoring or observations of these trees, we classified inoculated coast live oak into one of 3 groups. The first was most resistant. So these are trees, so to start off, all trees that were artificially inoculated showed some symptoms of sudden oak death. Might have just been some very small point bleeds on the outer bark, or could be more extensive bleeding cankers. But in this case, most resistant trees, these are in remission. So they once showed symptoms of the disease, so bleeding exudate, but they appeared to recover. Many of these trees form callus tissue on the cankers, and in all cases, we never considered a tree to be resistant if it had also been attacked by bark and ambrosia beetles, since we know from past research that attacks by bark and ambrosia beetles actually facilitate mortality. Our next group was intermediate. So these are trees that continue to show symptoms of the disease, and or maybe they stopped bleeding, but they had evidence of beetle attacks, but they were still alive. And our final group is most susceptible. So these are trees that died. This could be just death of the crown, so browning of the foliage, or the tree could have snapped. In cases where the tree snapped, this was consistently associated with evidence of bark and ambrosia beetles, so you would see actually lots of beetle tunnels and fungi growing in those snapped trees. So how did the distribution of these 3 classes change over the course of our study? So we see in 2010 that basically 2011, so about 1 year following inoculation, all the trees showed symptoms and were in that intermediate group. Very few trees had died at this point. But by 2012, we begin to see a more clear separation amongst the 3 groups. And actually by 2013, we see that the proportion of resistant trees within Barones is about a quarter. And in fact, up until 2017, we actually see that this proportion of resistant coast live oak, or most resistant coast live oak, seems to plateau. So we're confident in saying that about a quarter of the coast live oak that were artificially inoculated within Barones amongst our 2 sites appear to be naturally resistant to pathogen. At the same time, we see that the proportion of most susceptible or dead and dying trees increases, but also appears to plateau. So now we're at a point in time where we're not really actually seeing many changes in the classes of trees, which is good because it suggests that the trees that we believe to be resistant are probably in fact resistant. Now, in a previous study, we looked at the relationship between canker length and whether or not the tree was classified as most resistant or most susceptible. Unsurprisingly, we found that trees with larger cankers were most susceptible trees had significantly larger cankers than most resistant trees. And we saw this over 2 different periods, which 2012 and 2014. So based on that notion that canker length is associated with resistance, we wanted to look at the probability of resistance in 2017, so about 7 years following artificial inoculation. And we can see that as external canker length increases, that the probability of resistance 7 years following inoculation decreases. And so here, this is a logistic regression model the dashed lines indicate 95% confidence interval, where the solid black line is our logistic regression model, and the red diamonds you see are actually actual probabilities of resistance based on binning of trees in these sites. We did a follow-up analysis called a receiver operated characteristic curve to make sure that our predictions were different than chance, and this value area under the curve is very high, suggesting that these results are robust and reliable. Similarly, we looked at the probability of survival. So this could be trees classified as most resistant or in that intermediate category. And as with the probability of resistance, we saw that as external canker length increases, you see a decrease in the probability of susceptibility, which is not surprising given that our definition of resistance is very closely tied to the size of the canker. And actual probabilities of resistance in red closely follow that predicted probability line. So next I'm going to shift from the efforts that we did to examine resistance and classify trees as resistant over this long study period into how do we actually look at this resistance across larger scales. So as Bryce was mentioning, there's a lot of tree coast live oak in these East Bay regional parks. We obviously didn't include all of the coast live oak at Barones in these two sites in our study. So in total, we followed about 600 coast live oak trees over this 7 to 8 year period. And of those 600 trees, only 150 were actually artificially inoculated. So it's a relatively small proportion. So we wanted to see, can we actually maybe extrapolate or visually assess the patterns of resistance and susceptibility that we saw in these two areas over broader scales. So this was work done in collaboration with Horacio Lopez Nincora, who was formerly a postdoc at Ohio State, but now is a professor down in Paraguay. And so we asked the key question, what is the distribution of resistant trees in Barones? So to do this, we first had to delineate the two different sites, so that's Seaborg and Tabletop. So we used the convex hull technique to delineate each site. And what we did in this case is basically we wanted to define the smallest area defined by the trees that we had artificially inoculated. So the trees that were artificially inoculated that are included are indicated by the different dots, either red or gray. So this is the Seaborg site. We had about 88 trees here that were artificially inoculated, which, looking at the Barones, is just right down here. So next, we performed an analysis called the inverse distance weighted analysis to actually look at the spatial relationship between susceptibility or resistance and the distribution of the trees on the landscape. So pointing out a couple things. So hopefully everyone in the back can even see this, but we have a different color from light to dark gray. So that corresponds with the canker size. So in this case, we did this spatial analysis based on the canker length that was measured approximately 1 year following artificial inoculation. So lighter colors are associated with smaller cankers, which we know is associated with more resistant trees. And darker colors are associated with larger cankers, which is associated with more susceptible trees. The dot color corresponds to whether or not the tree was alive or dead in 2017, so that's 7 years following artificial inoculation. And where the dark dot is those trees that are alive, and the red dot are those that were dead. And so we did this in part just to see if the mortality status of the tree was associated with the results of our spatial analysis. And what we can see here is that there appears to be pockets of more resistant trees and also more susceptible trees indicated by darker colors for more susceptible, and more resistant is the lighter colors. And when you overlay that with the mortality status of the trees in 2017, we see, unsurprisingly, that those trees that are more resistant are still alive in 2017, whereas those the areas where there's more susceptible trees, there's dead trees present in 2017. Now this was at Seaborg site. We also performed the same analysis at Tabletop. They're just on different maps, just due to the geographic separation of the two locations at Briones. And we see similar results, even though our sample size is a little bit smaller, only 62 trees were included here. But you see there's pockets of more resistant trees and pockets of more susceptible trees. So we did a follow-up analysis called Moran's Eye, and this just confirmed the results that we saw, that there was in fact a spatial aggregation. So I also said that we use this opportunity to look at the incidence of natural coast live oak infections over time. And what we found, unsurprisingly, is that the incidence of natural infections increased, likely as a product of the disease moving into the area. At the initiation of the study, none of the trees in our study site had any symptoms of infection, but trees in nearby locations did. So we can see that it increases from about 2% in 2011 all the way to about 13% in 2017. We see a relatively large jump towards the end of this period, which corresponded with the end of the drought in this area and the increase in rainfall. So, in conclusion, resistant coast live oak exist. We found that about a quarter, or 27% of the trees in this study were classified as most resistant 7 years following inoculation, which is definitely promising considering that the rate of resistant trees in tan oak, for instance, is much less. We found that canker length measured less than 1 year following infection could be used to predict resistance and survival 7 years following infection or inoculation. Based on our spatial analysis, we found that resistant susceptible trees are spatially aggregating. This could suggest, as previously concluded, that there's a genetic component to resistance, although there could be an interaction with environmental factors as well, which we didn't necessarily specifically measure in this study. But this shows great promise, particularly for identifying resistant trees on the landscape, but also protecting resistant trees. So if we can identify these pockets of resistance, we can target them for collecting seeds for restoration efforts and also protect them against habitat encroachment, fire, or other issues. So unsurprisingly, we saw the incidence of natural infections increased over time, and both this combined with what we know about resistance has important implications for breeding and disease management. So with that, I'd just like to quickly acknowledge our funding sources, the USDA Forest Service, also state and federal funds appropriated to the Ohio Agriculture and Research Development Center, and of course the East Bay Regional Park District for allowing us access to briefings. So if there's any time, I'll be happy to take